So back in the very old days when we started to make things, then we didn't have any tolerancing. And so if we go all the way back to the Egyptians, they would have some sort of a plan or a design for what the pyramid was going to look like, but they didn't have any tolerances. They just had a general plan, and they might have some dimensions. I think it's the Great Pyramid that's 440 cubits on each side, and it's 280 cubits tall. But there's no tolerances, and just how well the different stones had to fit together was part of the craftsmanship, and you basically beat the slaves until it fit well enough together. There was no tolerances at all, because there really wasn't a need for it at that particular stage. As we come up towards the end of the 1800s, so let's say somewhere around, let's call it 1880, we start to see mass production. And we, in particular in the weapons industry, start seeing mass production. We see things like, here's Mr. Gatling's patent drawing for his gun. And we see that we start wanting to be able to have interchangeable parts. So we can make a series of each of the parts, and then we can take random parts out of these series and assemble them, and they will fit together. And so that might be something like, maybe we have a part something like this. And we have another part like this. Maybe this is a barrel, and it's kind of a short barrel, but you get the idea. And of course, we would like to have the barrel be able to fit into this end piece. And so to do that, and to make sure that every barrel fits into every end piece, so we don't have to select them individually and fit them, then we start to use dimensional tolerances. And so we might have here, let's say, maybe it's a diameter 100, and maybe it's plus 0.2, and plus 0.1. So we have it that it's a little over 100, and so we may put a tolerance on the barrel here and say that has to be, again, it's a diameter, and so it's 100, and maybe the top tolerance here is plus 0, and the lower is minus 0.1. And so by keeping those dimensional tolerances, we ensure that we can fit this barrel into this end piece. And as long as the form errors are fairly small, and at the time we were able to make parts with relatively small form errors compared to the ability of us to make dimensional tolerances, then we could make batches of these parts, and each of them would fit into the opposing part. So with dimensional tolerances, we can make interchangeable parts, and that works for a while, but then it's realized that there's still some limitations. And as a result, Mr. Taylor gets his patent. And as you can see, this is from the actual patent. It's issued in 1905, and it's for full form inspection of thread. And from that, we get what we refer to as the Taylor principle. Or these days, we also refer to it as envelope requirement. And it came out of problems with having things fit together. Say we have a part with a hole in it. So here's the part with the hole in it. And then we have the shaft that has a shaft that has to fit into that hole. And that shaft may have a bit of banana shape to it. And say that we have made the tolerances so they should fit together. So maybe for the hole here, we have given it a dimension, so maybe the tolerance is a diameter of 10, and it can be plus 0.1, and it can be down to 0. And maybe the tolerance for our cylinder here, our shaft that has to fit into it, maybe the tolerance here is again diameter of 10, and maybe that's then plus 0 and minus 0.1. So in principle, they could both be 10 exactly, which means that they should fit together. But if the shaft here is 10 exactly, but it's crooked, then everywhere we measure, we may get 10 millimeters exactly, but it still doesn't fit into the hole where we want it to fit. And that was what Taylor was contemplating, and that's where we get the Taylor principle. And what the Taylor principle does is it creates a full form inspection. And so what it says is that if we have the shaft here, and it has its form errors, then to be accepted according to the Taylor principle, it had to fit into a perfect counterpart like this at the upper tolerance limit for it. So this is a perfect cylinder with a diameter of 10.000. That's the idea, that at the maximum material limit, it has to fit into a perfect counterpart. And the same way, if we have the part with the hole in it, we have to be able to fit a perfect cylinder inside that hole, and where for the shaft we took the upper limit, for a hole it's the lower limit we take. So again, it would be a shaft, or plug gauge is the way we actually measure it, of a diameter of 10.000 that has to be able to fit through the entire hole. And so you can see, when we have that requirement, we can make sure, when we choose our tolerance values accordingly, that these two pieces can fit together and we don't run into the problem with the crooked shaft, because we have said we don't want that. It has to fit into a hole like this. And that was in the next development in tolerancing, the Taylor principle that, as I said, we get in 1905. So the next thing that happens is that we get up to the Second World War, so we get up to about 1940, and there we start seeing some much more high performance product, and where we start, for example, with the aircraft engines. Here's the Merlin that were in the Spitfires and the Mosquitoes and the Mustangs and a lot of the famous aircraft. And they were made decentralized so that parts are made in different places, and then they had to fit together when they came together. And they didn't just have to fit, they also had to be able to move against each other and work more than just being able to move. And when we look in the engine, we have the cylinder bore. We have a number of them. Actually, we have 12 of them. And then we have the bearings down here for the crankshaft. And there are some bearings along the way, but then there's the last bearing is sort of down here. And if we then look at the axis created by the bearings and the axis of the cylinder, then we want those two to be perpendicular to each other. And with dimensional tolerancing, we don't have any way to communicate that, but that became a necessity when we were going to have to build something like this. And so the way that took place was that we started getting some rudimentary geometrical tolerances. And so if we have the cylinder here, with its axis, and we have the bearings down here, and of course there are more bearings, but I'll just draw the two extreme ones. And they form an axis as well. Then with the first kind of rudimentary geometrical tolerancing, we could put a tolerance like this, where we say we want perpendicularity within a certain amount, let's say diameter 0.1, and we want this axis to be perpendicular down to this axis. And so that was the first way that we could say that with the blue axis here as the reference, we want the red axis to be perpendicular within a certain tolerance. And so that was the start of geometrical tolerancing, and it really stayed at that kind of a level up until close to 1996, when ISO TC 213 was formed, and where we've had the significant upgrades that came with the GPS system that we're going to talk about in this course overall.